Hello students, welcome to JEE's chemistry classes, the smartest and easiest way of learning concepts. In this video, we are going to discuss about the hydride shift and methyl shift in organic chemical reactions. So in many chemical reactions taking place in organic chemistry, come across with the more stable carbocation intermediates. Generally the carbocation intermediates. So first of all, what is this carbocation? Let us see. You know, the carbon having four bonds, four covalent bonds, that is sp3 hybridized. This is tetrahedral geometry. And if one of the bond is lost, it becomes carbon having three bonds with a positive charge, that is called carbocation. And this is sp2 hybridized one, and the geometry is trigonal planar. This is your carbocation. There are different types of carbocations here. All the three bonds in around this carbon having hydrogen, that is methyl carbocation. If two of the bonds are satisfied with hydrogen, one is carbon, then it is primary carbocation. If two bonds satisfied with carbon and one with hydrogen, that is secondary. If all the three bonds are satisfied with carbon, no hydrogen, that is your tertiary carbocation. So in many chemical reactions, this carbocation obtained as an intermediate, formed as an intermediate, and this carbocation stabilizes itself to form more stable carbocation. Yes, the stability of carbocations differ. You know, the stability of carbocations is in the order like this. That is, tertiary carbocation is more stable than secondary carbocation, which is more stable than primary, and which is more stable than methyl carbocation. The stability of carbocations is due to hyperconjugation effect. Okay. So in chemical reaction, if any of the carbocation formed as an intermediate, it will stabilize itself. It will rearrange itself to form more stable carbocation by using certain shifts within the molecule. Those shifts are called hydride shift and methyl shift, and in addition we have some more shift like a phenyl shift like that. But more often we use hydride shift and methyl shift take place in chemical reactions. Let us see an example to illustrate this. I have an alkene and a hydrogen bromide, HBr, hydrogen bromide, and how the reaction happens. What is the product? Let's see. You know, this is a double bond, a sigma and pi. The pi bond is weaker, and here H, it is a polar covalent bond. Br is more electronegative. It bears a partial negative charge, and this is a partial positive charge. This pi bond is electron rich, acts as a nucleophile, and this is electrophile. So the attacking take place like this. Therefore, this bond taken by this Br. Now I write like this. So when this bond attacks this hydrogen, there are two possibilities actually. You know, this carbon and this carbon. This pi electron is between these two carbon, and this is electron pair like this, the shared pair of electron between two carbons. So this electron can attack this hydrogen in two ways. One of the ways is that this carbon takes this electron also and attacks this hydrogen in this way. So it attacks like this. So this electron bonded with this hydrogen. Or it may also like this. This electron go like this. There are two ways. You know, this electron go like this. This electron bond with hydrogen, or it may go like this. This bond with hydrogen. So write two possibilities. So in this case, it comes like this. So it goes like this. This bonded with this hydrogen. And the other case is that and here is the hydrogen. This bears a positive charge. This electron comes like this. So this bonds with hydrogen. This carbon gets positive charge. Now look at this carbocation. This is your secondary carbocation. This is your primary carbocation because this is attached to two carbon. This carbon attached to two carbon, secondary carbocation. This carbon is attached to only one carbon. This is primary carbocation. So this is your more stable. And I take this more stable carbocation here. So usually in bond line structure, if you do like this, it is understood that is hydrogen, CH3 it is. Now it is a carbocation. This is secondary carbocation. And this carbocation, and here comes the important point. If this carbocation is whether it able to rearrange itself to form more stable carbocation. Let us see whether it can rearrange itself to form more stable carbocation by using certain shifts. So how this happens? So this is a secondary carbocation, and we have a carbon over here, 1, 2, 3 valency, and fourth with the hydrogen. Okay. If this hydrogen takes this electron pair, this hydrogen takes this electron pair and becomes hydride, H minus, hydride, and shifted over to this carbon to neutralize the charge. And this hydrogen comes here now, like this. Already you have a methyl group over here, and a positive charge comes over here because the electron pair is shifted with hydride ion as a hydride ion. So you get a carbocation over here. So this carbocation nature is tertiary carbocation, which is more stable than the secondary one. How the rearrangement take place? One of the hydride ion from this carbon shifted to this hydride ion shifted to this carbocation, and yields a more stable carbocation. This is tertiary one, and this is called hydride shift. Right? This hydride shift is known as 1,2 hydride shift. This 1,2 doesn't mean that any IUPAC nomenclature like that, because this is just implies the position of arrangement of shifts. Hydride and the carbon are vicinal to each other, adjacent to each other. Therefore, 1,2 shift is happening, hydride shift. Right. What happens if this alkyl group shifted instead of this hydride? Let this hydrogen be here. If this alkyl group shifted over here, again you will be getting a carbocation, but its nature is secondary carbocation. So you have to decide whether which shift has to be taken place. Which shift has to be taken place to yield a more stable carbocation. Here both shifts are possible, hydride as well as methyl beta. But if methyl shift has happened, it becomes secondary carbocation again. Again it will be unstable. Therefore, in order to stabilize itself, the hydride shift has been taken place. Thank you. So, in the previous example, we have a substrate and the reagent, alkene plus HBr. We got this product, and not this product. This is your wrong product. So, this product is as a result of hydride shift. And this hydride shift happened. How it is happened? This hydrogen, and here a carbocation here. This hydrogen shift, this hydride shift over here. So this kind of hydride shift is called 1,2 hydride shift. Here the 1,2 doesn't mean that your IUPAC nomenclature numbers. This 1,2 simply implies that the position of hydride ion and the carbocation are in vicinal positions. This 1,2 position, that is why it is known as 1,2 hydride shift. Now let us see another example which is similar to this, and which shift over here happens. So first thing, the partial positive, partial negative, attach this, and here goes like this. So we have a carbocation. Straight away I write one carbocation which is stable, and that is secondary carbocation I used to write. Okay, and here I have 2 carbons. Okay. Now this is secondary carbocation. Just to see whether this carbocation able to rearrange itself to form a more stable carbocation, that is tertiary carbocation. If it is able to form tertiary carbocation, it will form by using certain shifts, I told. But here, this is secondary carbocation. Okay. Now here we have one methyl group. This alkyl group, along with its electron pair, gets shift to this carbon to satisfy its positive charge. Therefore, what happened? This carbon gets positive charge now. whereas this methyl shifts over here. Now, what is the nature of this carbocation? 1, 2, 3 carbons are attached. Therefore, this is your tertiary carbocation. Now, this Br minus, right? Along with this, you have Br minus. So, this Br minus attacks here to form right. So, this is your alkyl shift. Generally here, which alkyl group is shifted here? This is methyl. So, it is methyl shift 1, 2 methyl shifts. Let us see one more example of the shifts. This is 3-methyl butane 2R plus HBr. So what happens in this? Our expected product will be like this. Just nucleophilic substitution reaction. So we expect a product like this. But what happens? The actual product will be due to shifts. So this oxygen has lone pair of electron and this partial positive charge, partial negative charge. So it attacks this nucleophilic attack. So this bond goes like this. So we will get like this. And this oxygen, since it has lost electron to this hydrogen, and this becomes a positive charge. And you know Br minus comes out. Now this oxygen has positive charge and needs electron and takes this electron pair towards itself. So it will give a carbocation. Now this carbocation is your secondary carbocation. Is there any chance of undergoing stabilizing itself by shifts? Let us see. So this is your secondary carbocation. And here we have one carbon. Here this is another carbon, and here now 1, 2, 3, fourth valency will be hydrogen. So let us consider two kinds of shifts here. What happens if this hydride shifted over here, and what happens if this alkyl shifted over here, and which shift gives more stable carbocation? That shift will be predominantly take place. For example, if this hydride shift takes place, what happens? You have positive charge here. Or if this methyl shift takes place, instead of this hydride shift, this methyl shift takes place, what happens now? Like this it will happen. And here you have methyl group. Yes. And which is more stable carbocation here? This is your tertiary carbocation because this carbon 1, 2, 3, 3 carbons. Here this is secondary carbocation because this carbon attached to 1, 2 carbons. So it is secondary carbocation. So tertiary carbocation, how it is obtained? Using hydride shift. And here the secondary carbocation is obtained by methyl shift. So which shift predominantly takes place to get more stable carbocation? The hydride shift will happen. So this is your carbocation obtained. And this will not form because it is less stable. So this tertiary carbocation getting attacked by bromine to form this product. In certain cases, such as in cyclic systems, the intermediate is stabilized by ring expansion. The intermediate is stabilized by ring expansion process to form more stable product. Ring expansion in the sense, if a 4-membered cyclic ring is converted into 5-membered ring, or 5-membered ring is converted into 6-membered ring, this kind of process is called ring expansion. Usually, a 6-membered ring is more stable, highly stable, than a 5-membered ring, then 4-membered ring. Because in 6-membered ring, the bond angle is perfect and it is more stable due to minimum strain. Let us see how this ring expansion takes place in such compounds. Let's have an example. So for this, your expected product will be like this. But what the actual product is? So first is a polar covalent bond. Here is more electronegative. It moves towards itself. So it forms a carbocation. And this carbocation is a secondary carbocation. And this is a 5-membered ring. Here the ring expansion takes place to form more stable 6-membered ring. How it happens here? So this 2 carbons have a bond between them. This electron pair gets shifted to this carbon to form bond. So you write as it is. This electron pair like this. Now it is going to shift like this. Therefore I write like this. So once it shifted like this carbon has lost its electron pair because it happens like this. This carbon lost its electron pair, so it forms a carbocation. Right? Now, I arrange properly to form 6-membered ring. In order to obtain it easily, you can number it. Number in the sense it's not IUPAC system, but you can write easily from this species to this species. 1, 2, 3, 4, 5, 6. Okay, write as it is. So this is your 1, this is your 2. Between 2 and 3, this bond forms. So 3, 4, 5, 6. And arrange it properly. This is your intermediate. Arrange it properly. So your 1, let any carbon be 1. So 1, if this is 1, this is 2, 3, 4, 5, 6. In first carbon you have carbocation. In second position we have 1 methyl group. So this is your secondary carbocation. Now the compound is stabilized using ring expansion. And one more thing, this carbocation is further stabilized. This carbocation is again stabilized by which shift? To form more stable carbocation. Because you can see here, initially the secondary carbocation is formed. This is a secondary carbocation. Upon ring expansion also, it remained as a secondary carbocation. And this secondary carbocation stabilizes itself to form more stable carbocation, by which shift you have to decide. So here we have 1 methyl group, 1 hydrogen. Which shift happens such a way that, so that it forms more stable carbocation. If hydride shift happens here, if this hydrogen comes here, now the carbocation gets. This carbon becomes carbocation. If this alkyl group comes here, again this carbon becomes carbocation. Now which shift is preserved? So hydride shift, methyl shift. So upon hydride shift, what happens? This kind of thing happens. This hydrogen shifted here, this carbon get neutralized, and this carbon becomes positive charge, carbocation. And this is your tertiary carbocation. If methyl shift happens, if this methyl shifts here, what happens? This is again secondary carbocation. So which is more stable carbocation? This is your more stable carbocation. This is less stable carbocation. So the product formed will be like this. This OH minus, so this is the actual product of this.